Hello everyone, thanks for joining the APN Digital Summit. We hope you've enjoyed the presentation so far. Before we get started with our presentation, we want to go over a few housekeeping items. First, this session is being recorded. We will send you the recording when the presentation is over, along with the additional information to help you continue learning more about these services. If you do have questions during the presentation, please add them to the question window. We will do our best to answer all the questions as they come in, but if we don't, we will follow up in an email after. If you're having any audio issues, try using your computer's mic and speakers. This usually fixes the problem. Thank you again for your time today. I am now going to pass it over to our presenter.
Hi, everyone. Thanks for joining us for the serverless migrations pattern session. My name is Mike Deck. I'm a partner solutions architect working with all of our ISV and consulting partners who are building solutions and services on top of or integrated with our serverless platform, like Lambda and API Gateway. And today I wanted to spend a little bit of time talking about various patterns for migrating workloads from either traditional on-premises infrastructure into a serverless application model, or potentially looking at even how you would go about kind of migrating from various other architectures into a serverless mode. And I think, when people think about this process, oftentimes there's this idea that, there's kind of this general continuum of how modernized your application can be, with serverless being kind of the end goal for a lot of customers, and kind of the legacy on-prem type applications being at the other end. And I think oftentimes people think that these are actually sort of steps in the process where, I need to start off on-prem, and I'm going to lift and shift that into a standard just sort of EC2 based architecture. Then I'll work on sort of modernizing it, making it more sort of cloud friendly, and then potentially go through a step where we containerize it and put everything into Docker. And then finally, we can make that last step into serverless. But I would argue that, this approach has some drawbacks in terms of the kind of costs that you're incurring at every one of these transitions. So really, when you think about it, there are a number of different sort of costs and risks that you're having to deal with every time you make one of these types of transitions. And so looking at options for, hey, how do we just go straight from a legacy architecture and leapfrog directly into serverless is actually an approach that I think bears evaluation at the very least, if not should be something that you consider to be the sort of standard model for how you help customers move from kind of legacy applications into the serverless world. That's not to say that every single application that you come across in your customers' portfolio is going to make sense to move directly to a serverless architecture. And in some cases, you're going to want to do things in a more incremental approach. But I think oftentimes we've seen this actually where customers have decided to take a much more aggressive stance on this. And they're able to eliminate a lot of the cost and risk associated with doing a much more kind of incremental approach that also gets them to sort of their final destination a lot faster. So the issue with this, and really with any kind of migration project, regardless of whether you're targeting serverless or even if you're just doing a lift and shift, is that oftentimes we don't have a chance to shut everything down cleanly and kind of take our time in migrating a system over into a new architecture. The production system is up and running, and you really can't stop the business just to make this kind of IT transition. The other thing that makes this particularly challenging within the context of serverless and within the context of AWS Lambda in particular is that you really can't lift and shift. There's really no good option for taking an existing legacy code base that was written and intended to be run on top of on-prem servers and just lifting and shifting that exact same code base or executable into a Lambda environment. The Lambda execution environment has enough kind of specific constraints that it requires in terms of how you manage state and how you ingest events and how you sort of run processes, et cetera, that just typically doesn't make any sense to even attempt to approach it that way. Now, there are definitely cases where certain libraries, certain core processing functionality that's been developed and packaged into its own sort of standalone library. I've got several customers I've worked with on kind of engineering simulation type systems where they've written some native compiled binaries that do this very complex math and things like that. And then really the rest of the system is a very, very thin wrapper around some of those things. And so being able to kind of lift and shift some of that code and leave it untouched is often possible. And you sort of just have to rewrite kind of that wrapper code and migrate it from kind of the on-prem stuff to Lambda. But when you really kind of think about a traditional lift and shift operation, that's typically not going to be possible in the serverless world. So talking about sort of some of the other approaches that I've seen customers try in the past. You've got sort of an existing legacy on-prem app with a bunch of servers that's all sort of deployed this way. You can spend a lot of time kind of re-architecting and re-implementing the entire system from scratch using a serverless architecture, which oftentimes is kind of part of this process. Is you really do need to start from a blank sheet of paper and understand what is the goal, like where are we trying to get to from an architectural perspective. But going and actually building that full thing in AWS and getting a completely functional system in the cloud, and then trying to sort of just flip the switches one day and turn off the on-prem version and turn on kind of the new cloud-ready version of your application is typically not the best approach. So trying to go with this kind of big bang integration oftentimes ends with disaster in a lot of cases, just because there are a lot of things changing, a lot of moving parts going on all at once, and that really kind of tends to be difficult to appropriately address all of the various risks that are out there when you do it that way. So really the question becomes, okay, so how can we mitigate the risks? Because the goal that we're trying to achieve is relatively similar to that picture. We want to move from kind of this on-prem legacy architected thing into something that is architected according to kind of cloud native best practices, using a lot of these managed services. So the architecture of the system itself is going to look very different. We expect to have a lot of new code that's going to be developed as part of that. But the question around how to do serverless migrations, in my mind, isn't as much around how do you actually do the architecture itself, although there are certainly aspects of that that are important. But it's really how do we actually kind of devise a process in which we can mitigate a lot of the risks that are involved in kind of flipping the switch here, and how can we do that more incrementally and do it in a way that allows us to control things in a much more intentional way. So let's take a look at some options for doing this more incrementally. So if we kind of drill down a little bit further, most legacy applications look something like this. You've got a number of different sort of request paths that sort of come in the front door. You've got this giant monolithic application that sits in the center that then makes calls out on the back end to a number of different, whether they be databases or other kind of external services. And so really the question is, how do we kind of migrate all of the clients that are sitting on the front end, talking over these various interfaces, using these various different APIs that come into our system, and enable these clients to migrate off of the legacy application, and then make it easier and less risky to replace the back end that we've got. So one of the kind of classic patterns that gets used in these types of migrations is a Façade pattern, and to a certain extent, this is also referred to as a strangler pattern, the way that we're really kind of implementing things. And so basically what happens is we introduce this Façade in front of the legacy application, so that now instead of our clients actually hitting the legacy application directly, we sort of incrementally roll out this Façade for our clients to hit. And the Façade itself is doing very little in terms of actually implementing any business logic. Instead, what it's doing is it's exposing this kind of unified API in the front and taking care of any potential peculiarities of the legacy application's API, and providing something that's closer to what we expect our long-term kind of target API to look like. And basically, this gives us the ability to slowly migrate clients over, so we can have, one of our clients migrate to the Façade while the others are still working on kind of any compatibility issues that we may have. It gives us an easy way to roll back if there were a problem. So if we were to go through one of these migrations and set up one of our clients to hit the Façade, and there's a bug that arises because of that, it's very easy to roll back and instead point the client back to the legacy API while we fix that. So you're able to sort of run two versions of the API, if you will, in tandem, kind of using this this type of model. And so once you've done that, now all of your clients are talking to this kind of Façade using this new API layer, and that allows you to now start building out the new application backend to fulfill some percentage of those requests, again, in tandem with the legacy application. So now we can kind of, over time, re-implement pieces of the legacy application, and eventually get to the point where now we have this very clean architecture where we've got a nice, well-architected API on the front end, as well as a clean integration then to our serverless application in the back end. And we've been able to roll that out in this incremental fashion and sort of subsume the entire legacy application during that kind of whole process. So when we take a look at this this pattern overall and kind of map that into, okay, what does that really look like from a technical perspective? The service that I think makes the most sense to talk about is API Gateway. So Amazon API Gateway, if you're not familiar with it, is a service that allows you to define HTTP RESTful APIs and serve those APIs on the back end using a variety of different backends. So you can use both Lambda functions if you want a completely serverless implementation, as well as integrating it with other HTTP endpoints that are running inside of AWS. So this might be something deployed on top of EC2 using Elastic Beanstalk, or on top of an ECS cluster if you've got a containerized application. But it can also be used to front any other HTTP service that's available on the internet, or even within your VPC now. And then this can also be used for other AWS services. So if you wanted to use something like a Kinesis stream and expose that Kinesis stream directly via your custom API, so using custom domain as well as custom resource names and methods, that's also supported as well. So basically, API Gateway gives us this ability to now implement this Façade that we were looking at previously. We're now in the middle of our clients and in our backend application. We can introduce an API Gateway, and then on the backend, we now have the ability to point that API at both our legacy backend as well as Lambda functions or other serverless options. So taking a look at kind of our previous example in terms of how this would really look in reality, kind of migrating an API that's currently running on-prem. You probably have a number of clients that are currently running on-prem that are hitting your legacy application directly. So the first step would be to update the API, update the clients to hit this Amazon API Gateway instance that is being backed by the legacy application itself. So again, we're not introducing any kind of real changes to the business logic. There's no update to the code itself that's running this application. It's really just about kind of switching the endpoints that the clients are talking to. And again, in some cases, we might also be doing kind of manipulations from kind of a structural level in terms of what the actual requests and responses look like. Potentially changing the schema of these messages that are getting passed back and forth in order to make it more amenable for our migration down the road. But the primary goal here is just to kind of update this, update the client, so we have this layer of abstraction now between the clients and the legacy application, so that it'll make it easier for us to move functionality going forward. And then once we've gotten all of the clients migrated. So in this diagram, I'm not sort of showing the incremental updates, but really sort of the broader milestones of just getting kind of all of our clients migrated onto API Gateway. Once we have that ready to go, then we can flip the switch, if you will. And again, we can flip that switch incrementally if we want, to where we're updating just single resources or single methods on our API at a time, to be backed instead by Lambda functions or by a larger serverless application on the back end that's providing the same set of functionality that our legacy application did, but now implemented using a more modern architecture that takes advantage of all of the great kind of cloud native features that we've discussed. So one of the big things that you have to think about as you're going through this, so assuming you're using this kind of strangler pattern to incrementally migrate clients of an existing application over to a new system, whether that's implemented using a serverless architecture or any other, one of the things that is very much unique to the serverless application world when we're talking about these types of migrations is how to handle the data layer of the application itself. So re-implementing the actual business logic and functionality that lives inside of your Lambda functions, taking and updating the code itself, is certainly an important part of the entire discussion. But then one of the really critical pieces of this too is making sure that we get data migrated appropriately, and that our applications are able to continue running. As we kind of talked about previously, we're sort of changing the wheels on this race car as it's driving down the track. And in order to do that successfully, we need to make sure that the data itself is staying consistent within the context of that migration. So there's some interesting challenges when it comes to building serverless applications with kind of legacy databases. So again, oftentimes you've got a legacy application where the database is deployed inside of your on-prem data center. And that becomes problematic when we're talking about using a Lambda function to talk to these databases, because typically you don't want to expose those databases to the internet, which is really kind of what Lambda needs typically when you're launching a Lambda function. It's typically going to be using internet-enabled endpoints such as DynamoDB and other kind of cloud-based services. However, there is certainly the option for deploying your Lambda function inside of a VPC instead of using the sort of default VPC, which only gives you kind of connectivity to the internet. You can associate your Lambda functions with a VPC that you own in your own environment, and then using sort of any of the standard connectivity mechanisms that are available, whether that be a VPN connection or using something like Direct Connect back to your on-prem system, those Lambda functions now have network layer access that they can use to privately access databases that are deployed to your on-prem environment. And so by using this kind of mechanism, you can actually keep the data that your legacy application is still accessing in your on-prem environment, and then still enable that new sort of serverless application that you've developed to access that at the same time. There are a couple of things to consider when looking at this type of architecture. First of all, function concurrency and connection management is a major consideration anytime you're dealing with serverless applications accessing kind of traditional or legacy databases. So the issue that you primarily run into here is that Lambda gives you this incredible ability to scale horizontally very, very quickly. So you can very easily launch 1,000 concurrent executions of a Lambda function, which results in 1,000 concurrent connections being made to your database and 1,000 concurrent queries being kind of executed against that database all at once. And typically, most legacy databases were not designed to be able to handle that kind of connection or query load against them, because they never expected for the code that was going to be accessing them to be running on more than just sort of the single server that's currently running in the on-prem environment. So as a result of that, you need to be very sort of cognizant of how your serverless application is going to scale, and how that's going to impact the database database that's being accessed on the back end. So keep in mind when you're sort of designing these things and setting up access to remote databases, the concept of concurrency controls that are enabled by AWS Lambda. So Lambda allows you to set a maximum number of concurrent executions for an individual function. By default, your functions will execute in as many. They will scale to the maximum number of concurrent executions allowed by your account, as wide as they possibly can in order to fulfill as many requests as you're sending. So by default, the account limits are 1,000 concurrent requests right now, and those can be raised even higher. And so without any additional kind of concurrency controls, you can expect that if you receive a burst of traffic or a flood of requests, you have the potential to scale very, very wide. However, you can set specific function-specific limits on the total concurrency as well, which can be used to protect those kind of backend endpoints. The other thing to kind of keep in mind is, your Lambda functions don't necessarily need to access those remote databases directly. And oftentimes what's a better idea is to set up some sort of proxy or cache for the on-prem database in the cloud in order to let your Lambda functions access that. So now you can kind of make a single copy of that data from your on-prem database using something like the database migration service as an example, and then let your Lambda functions now hit a database that's much more capable of handling the scale that serverless applications are able to manage. Obviously, managing kind of data consistency, if you've got multiple systems that are trying to write to the same data set, becomes tricky there. But if you're in the initial kind of process of doing a migration, oftentimes you're addressing simply the read operations, and that's often a really good kind of approach to use there. The other thing to be aware of is kind of the cold start latency that's associated with VPC connectivity when you're using Lambda functions. So if you're not aware of kind of the general execution model that Lambda uses, when you invoke a Lambda function, Lambda under the covers will create an independent execution context for each one of the concurrent invocations that occurs against a given function. So if you have 5 concurrently executing invocations of a single function, you'll have 5 separate execution contexts. Each time you create a new execution context, which usually happens because either you're invoking a function for the first time that hasn't been invoked in a while, or you're increasing the amount of total concurrency, and so there's no existing execution context that can be reused. Every time one of those execution contexts gets created, there's a little bit of what we refer to as a cold start penalty, just the amount of time that it takes the Lambda service itself to actually bootstrap the runtime itself, download your code, get everything initialized, let your code itself initialize as well. And in the case when your function is associated with a specific VPC, there's also a step that requires Lambda to go and create a new Elastic Network interface and do kind of a cross-account ENI attach from your VPC in your account into the Lambda managed environment. And that process takes a little bit of time and can add significant latency overall to the actual cold start invocations. So again, the cold start process is not happening on every single invocation of your function, but it does happen on a very small percentage, usually less than 1% of total invocations. But if you have sort of a lot of sensitivity to kind of that P99 latency metric, and you need to ensure that that the worst case latency for your service invocations is relatively low, that's something that you do need to be aware of as part of that migration, and really make sure that you're measuring that and understand what the latency characteristics look like before going down that path. So the other kind of topic to be aware of in a serverless context is this idea of event sources. So Lambda itself is an event-oriented service, and really serverless architectures in general are very much about understanding the various events that are getting produced by your system and then writing code to respond to those events. And oftentimes when customers are moving from legacy architectures into a kind of cloud native one, there are a number of different event sources that may not be sort of supported directly by Lambda today. So for instance, if you've got a traditional sort of JMS style message broker that's running in your on-prem data center, today Lambda can't sort of respond to native JMS messages that are inside of some message broker that you're managing yourself. That's not one of the native event sources that Lambda has. And so you need to come up with kind of a different mechanism for handling that. And there's a couple of different ways that you can kind of approach this. The first is to use kind of a polar function hooked up to a CloudWatch events timer trigger to periodically spin up another Lambda function that's responsible for reaching out to your on-prem message broker, polling to see if there are any events that have been delivered to a particular queue, and then turning around and handing that off to a processor function kind of downstream. So this is kind of a pattern that we saw a lot of customers use for a while when integrating with Amazon SQS before there was an SQS native event source. So there are a number of good examples of how to build these types of polars, actually. If you look for some of the applications in the serverless app repo, for instance, that deal with SQS integration, there's a number of good examples that you can take a look at for how to design one of these, and really the same overall structure and pattern that you would have historically used to integrate with SQS, which is not really necessary anymore, but the same pattern that you used to use is very much applicable in these types of environments as well, and that's a good option for you to take a look at if you are trying to build one of these types of services. The other option is to do more of a hybrid kind of deployment model. So again, Lambda functions are intended to respond to events. They're not intended to stay up and running indefinitely so that they can maintain kind of long-lived connections. And so if you've got particular protocols or legacy event sources that require that kind of idea, so definitely worked with a number of customers who have these, sort of industry proprietary type protocols that rely on this long-lived TCP connection, for instance, between a client and a server. And that single connection is held open for a long period of time, and data just sort of streams over that, and messages are kind of delivered directly that way. So there's no sort of concept of an HTTP endpoint that's getting pinged or anything like that. And so as a result, you need something that can actually live, a long-lived process that can establish that TCP connection and listen to these events. So in those cases, it makes a lot of sense to move to kind of a hybrid architecture where you have something like an ECS container or other process that's running on top of an EC2 instance that takes care of kind of managing the event integration piece, and then downstream invokes a Lambda function. And the reason for kind of continuing to use Lambda to do the actual event processing itself here is because oftentimes the event processing is kind of the computationally expensive piece of the puzzle. And so you can continue to rely on Lambda from a kind of scaling and reliability perspective, where it's going to manage provisioning and load balancing the requests that you receive across a managed fleet under the covers for you, so you're not dealing with that yourself, whereas you can keep a relatively lightweight cluster of servers that are still deployed in a high availability architecture running for just that kind of front-end event source integration. And so that reduces the complexity of that cluster that you need in order to manage the event source. And because there's such small amounts of kind of compute actually being used, you can process a large number of messages with this kind of event broker component that you've deployed on top of a container. And so it's not terribly expensive to run a couple of small instances in an HA kind of configuration in order to manage that. But then as the sort of workload increases and the really kind of computationally expensive part of the processing is done on Lambda, you can allow Lambda kind of scale up and down for you automatically and take advantage of all of those kind of cost saving that you're looking for from a serverless application. So I think one of the really kind of important takeaways from that is that serverless is not really, it's not an all or nothing type of proposition. So it doesn't mean that in order to do serverless, you have to be 100% deployed on top of Lambda and you can't ever use a container or an EC2 instance. There's plenty of different sort of compute options that are available on top of the AWS stack. And while AWS Lambda provides some really nice characteristics in terms of its scalability and availability and the cost model that it allows you to implement, there are certainly good cases where it makes sense to use other compute offerings. And we have a lot of examples of customers who've been very successful in deploying the core components of their workload on top of Lambda, but then using these various other compute services in order to manage other aspects where it just either doesn't make sense to actually migrate the code and kind of pay the cost that it would take to actually completely rewrite the application so they can run in Lambda, or they have these other kind of constraints around how the protocols that they're using work or the integration points that they need, and it just doesn't make sense to use Lambda from kind of an architectural perspective there. So I think that's really kind of the important point to take away from this, is that as you're looking at, how can we leverage serverless architectures to kind of improve the systems that we're building for customers, there are oftentimes opportunities that you can use Lambda, even if you don't necessarily migrate the entire system wholesale into a serverless architecture. So even if you're using something besides API Gateway to manage kind of the front end message processing of your system, maybe it still makes sense to use Lambda on the back end for pieces. Or similarly, even if you've got a containerized application that's doing the bulk of the actual compute for whatever reason, that doesn't mean that API Gateway can't provide valuable services or other aspects of the messaging and persistence services that are part of the serverless platform as well. So just something to kind of be aware of. We definitely hear a lot from customers and other partners sometimes about what does serverless really mean? Can I do serverless even if I've got components of my architecture that don't necessarily fit into Lambda? So the last kind of point that I want to make when we're talking about kind of migrations patterns in general is, there are a number of different kind of technical pieces of this, and certainly, this is a very sort of brief overview of just sort of some highlights of what you need to think about as you're preparing to do migrations of systems into a serverless architecture. But the other big thing to think about beyond the technical aspects is the people and processes. So, we talk a lot about the fact that things don't really change from the perspective of how you write code and a lot of the tools that you use to build and deploy code within a serverless application compared to your sort of traditional development models. But I do think that there are a number of cases where, organizationally, the way that the development organizations themselves are structured and the processes that they use, in order for them to really kind of take advantage of many of the benefits that serverless provides, there's definitely a large aspect of needing to ensure that the people and processes involved are also updating themselves as part of this migration effort, and not trying to just continue to use the legacy processes that were in place previously to manage a much more agile and much more kind of capable platform that you're migrating to. So kind of looking at sort of the way that organizations have historically approached application development, where you have developers who are sort of ultimately responsible for a large monolithic application. You typically have one code base that's built into a single large monolithic artifact, and then that artifact gets deployed onto a server. And really kind of this is the crux of the the monolithic architectural style. You've got a lot of developers that are all working against the same code base. There are a lot of integration issues that you run into, as well as just the speed at which you can actually do deployments becomes limited by kind of the slowest moving component within this overall architecture. And that's really one of the big kind of benefits that we see from customers moving to a serverless architecture, is this ability to be more agile and to get to market faster and to move more quickly. And so if you're continuing to try to use some of these legacy processes to manage software in a serverless world, you're not going to see the benefits of that of the platform from that perspective that you normally would. And so that's one of the big reasons why it's important to really kind of think about how are we kind of managing our applications, how are we managing the teams that are developing these applications, and what are the processes that we're using to kind of do that. And so, similarly, looking at how these processes are often implemented, you typically have developers who are using the exact same processes to kind of deploy their code to their local environments and doing local testing, as well as then turning around and interacting with kind of the cloud-based deployments directly. You've got the entire application sort of deployed entirely on your local development environment, and then that sort of same process is typically used in a cloud deployment. Whereas when you move to a more sort of serverless and microservice oriented architecture, you don't necessarily have every single one of the microservices that your particular piece of code needs to interact with running locally. And so being able to kind of manage environments at a higher level, understanding where kind of the various test environments exist and how those integrate across the sort of developer lifecycle, and how do we coordinate across multiple loosely coupled teams so that any individual team isn't blocked by another, is a really important kind of piece of the puzzle to think through as you're going through this kind of process. But again, just to kind of reiterate one of the things I mentioned previously, good development practices are still good development practices. So while some of the general sort of approaches that you use in terms of organizing teams change when you move from sort of monolithic application development and deployments into microservices, certainly the way that you're actually writing code and kind of the practices that you implement in terms of how you're building and testing the software itself don't necessarily need to change significantly, and you should continue to encourage people to improve in those kind of standard areas that we know that well, or the standard practices that we've developed as an industry over the last several decades. I think there's oftentimes a certain tendency for people to think that serverless just makes everything easier, and so that means that we can stop kind of thinking about how code gets organized and how we're really sort of developing software at the application design layer. But I think it's important to continue to invest in those areas and improve the quality of the software that you're writing from that perspective. And along those lines, investing in automation as a team is really going to be kind of the key to being successful from an overall people and process and organizational perspective. So utilizing tools like AWS Code Pipeline and Commit and Code Build, as well as AWS SAM, which we'll talk about in a little bit, are really going to be critical to being successful in the overall path here. If you're moving from a world in which developers are building these large monolithic applications and deploying them in a big bang kind of deployment model, and a lot of that is kind of manual processes that are maybe documented in runbooks and things like that. And now you move into a world where you've got dozens of microservices that are being managed by separate teams, and all of them are needing to get sort of deployed multiple times within a month, or potentially even multiple times a day. If you don't invest in kind of the automation and the groundwork to put in place all of the guardrails necessary to manage that, whole process in an automated fashion, it's going to be very, very difficult to be successful with that as you roll out the architectural changes that are going to be necessary in order to kind of get the overall benefits the client is looking for in terms of cost and agility and things like that. So definitely don't let the underlying processes necessary to do deployments and to manage the application as a whole be a blocker for making the kind of architectural changes that you want to. So that kind of wraps up everything that I've got for you today on the migrations front. Really appreciate your time today, and if anyone has any questions, feel free to enter it into the system, and we will try and get those answered before the end of the time. Thanks a lot.